So I want to talk about a fascinating number that relates to exponential functions. It's called Euler's number, and we represent it with the letter E. Okay, this person's name is Euler. It doesn't look like that, but that's how we pronounce it. And he's a mathematician, and he discovered this number E when he was looking at compound interest formulas, like making money off of interest at a bank. And he was developing some formulas and found a pattern, found an interesting function that he needed to evaluate or needed to find some properties of. And the function that he looked at was this 1 plus 1 over x raised to the x power. Now this function has a variable in the exponent, so it looks like an exponential function. But it also has a variable in the base, and the base is this complicated expression here. And so it's kind of like an exponential function, but kind of not. What he found, though, is that it does have a horizontal asymptote. Okay, so this thing has a horizontal asymptote. And he needed to determine what the value of that asymptote was. And what he determined was it was a value, it was a number that had some decimal representation that he couldn't nail down. In fact, it's something called an irrational number. It has a decimal expansion that doesn't terminate and it never repeats, so it just goes on and there's no pattern to it. Now, how do you figure out the value of a decimal that never terminates and never repeats? Well, we just give it a name and we just call it E, and then you calculate it to as many decimal places as you need. And so what he was able to do was figure out several decimal places. In fact, I think it's in the 20s of how many decimal places he figured out. But essentially the way we would say this is that as x goes to infinity or approaches infinity, now remember a horizontal asymptote is the horizontal line that the graph approaches as the x value gets bigger and bigger and bigger. And so as x approaches infinity, this function 1 plus 1 over x to the x approaches the number E, which Euler determined to be approximately 2.71828. And then of course there's an infinite number of decimals after that. Okay? Now this number is very important in mathematics. It shows up very often in calculus and is a very, very useful function when used as a base in an exponential. And so the function y equals e to the x is a very common function that you'll see in mathematics and very useful. It has very interesting properties that are unique to that function, which I can't really get into for this video, but they're very interesting. And so what I want you to see is that this base, this E value, 2.7 roughly, is bigger than 1. Remember, we talked about the base. If the base is bigger than 1, then we have an exponential growth function. And so this function, when plotted, is going to be, it's going to grow exponentially. It has a y-intercept of 1 because there's the coefficient here is, we don't write it in, but it's a 1. So it's got a coefficient of 1. And the base is greater than 1, which means that it's going to be growing. So we have a function that is always increasing. Okay, so that's roughly what our exponential, our e to the x, looks like. And so we will see this function show up quite a bit in the exponential section in our book, but also when we start talking about logarithms, it's going to be a very useful function as well. So Euler's number E, very useful, very cool, and lots of applications including compound interest and many other things later on that we will see. All right.